So it's 9 o'clock, so we're going to go ahead and get started. Welcome to TechStar's T3 Level Up conversation this morning. We're going to, I'm Phil Deaton, newest member of TechStar.
And I'm Joey Blair. I'm in field service here at TechStar.
Yeah. So Joey, how long have you been with TechStar?
Going on probably about 6 years now.
6 years?
Yeah.
Okay.
Yeah.
And what was your background?
So my background before this, I kind of did more PLC type work. It was a little bit more on the commercial side, a lot of electrical PLC type stuff, and then found my way over to TechStar, and now of course I do more of the nuclear and the different kinds of instrumentation that we deal with here. Do a lot of training here in our we have a training center next door, and that's where I do a lot of our training at.
Okay, very cool. And
yeah.
So I've been in the industry, I guess, about 5 years now.
Right.
Background chemical engineering.
Okay.
Was on the manufacturer side, now on this side with us. And so, yeah, Joey and I are going to kind of talk about nuclear instrumentation this morning, and specifically about our newest partnership with Berthold.
Yeah, we're real excited about it.
So let's go. So for those of you guys who aren't familiar, Berthold started in 1949 in Germany. They're a global leader in nuclear instrumentation, and really that's all they focus on. They are kind of master of their craft. Key focus is on radioactive technology, measurement technology, specifically level and density. So we're kind of going to go into, for the folks who aren't aware, how some of that stuff works and maybe some nuances.
Yeah, feel free to ask questions, and we'll just have a discussion today.
Yep. And so just so everybody's aware, there's a slight delay on the stream that you guys are seeing. So if you ask a question and it looks like we're not responding immediately, it's just the delay catching up, and we'll get to it at some point.
Right.
So like we said, Berthold began in 1949. They're a global leader in radiation-based measurement. On the slide here, what you guys see is just one of their products, one of their many products. This is kind of for the heavy industry, if you will, so the refining, the petrochem, really nice design instruments. But what they can do with the technology is level, density, imagine it, and they can basically accomplish it. Let's see. So how does the technology work? Okay, so what we've got basically for any radiation-based measurement is you've got a gamma-emitting radioactive source, typically. What that radiation does is cross whatever you're trying to measure. So whether that's a pipe, a vessel, you name it, it's crossing it. And what that radiation does is it hits a scintillation crystal. That scintillation crystal lights up in the presence of radiation. And so in order to convert that light signal to an electrical signal, what Berthold does is they utilize a photomultiplier tube.
Right.
Photomultiplier tube does what it sounds like, light to electrical signal. The detector can then output an electrical signal, which is a result of how much radiation did it see, right?
Right, yeah, that's exactly how it works. So for I guess for density, we are basically just shooting energy through whatever kind of substance we're trying to shoot it through, and measuring how much energy we're getting on the other side. And that amount of energy, we can say that at this amount of energy we have this specific density, and then we change that density and we have another specific density, and as that radiation changes, it's going to be relative to your density.
So the slide that everybody's looking at right now, this is basically on the detector side. So whether it's radiation aimed at it from a source that's installed by Berthold, or whoever, if it's background radiation, etc., any radiation that hits the scintillation crystal will cause the crystal to light up, which then the photomultiplier tube will then convert.
Yeah, and it sees it like in light, or counts. So it's like how many pulses of light is it seeing through there? Yeah.
So on this next slide here, what we've got is kind of a diagram of a real-world application, if that's what you want to call it.
Typical vessel, right?
Yeah. So what you can see here is you've got a source on the left-hand side of the screen, and that's that radioactive source we're talking about.
Right.
Let's talk a little bit about the source. So probably some of the most common elements to use are probably cesium-137, cobalt-60 are probably the two big ones in the industry.
Yeah, those are probably going to be the main two gamma ray emitters that we're going to have.
So kind of pros and cons of each. There are, hey, there's two. Why would you use one
versus the other?
Right.
Yeah.
So the benefit of cobalt is it's a higher energy source. So it can basically penetrate thicker walls, higher density material, etc. It's got a half-life of 5 years. Cesium-137, on the other hand, the downside is it's a lower energy source, but the benefit of it is it's a 30-year half-life. So when you're designing a solution for an application, you really got to look at, hey, do I need this higher energy? Is there a benefit to the Cobalt 60?
Right.
It's 5-year half-life. Does that fit the application? Or maybe the Cesium-137 is the right fit. The great thing about Berthold is they can offer both types of radioactive sources.
Right.
So that's really a core competency of Berthold is optimizing the solution for the application, and we'll kind of get into a little bit more of that in a bit.
So when will we use Cobalt 60 versus like Cesium-137? Is there specific?
So specifically, one example I know, a couple of examples that are great is really thick vessel walls.
Right.
The Cesium-137 is just not going to penetrate. Cobalt 60 is an advantage there.
So like a reactor or some type?
Like in the petrochem world, HDPE reactors, something like that. Or if you get a lot of NDT testing, NDE testing kind of in the background,
right.
A lot of what those folks use are cesium-based sources. If you're using a Cobalt 60 source for measurement, they can actually discriminate out because they basically have two different footprints, if you will. So if you know your measurement, what you're trying to measure is this Cobalt 60 energy, and you're seeing this Cesium-137 in the background, you can just discriminate it out and leave your measurement unaffected. So that would be another advantage of using it.
Oh yeah, that's pretty neat. So you can cancel out the Cesium-137 signals and the gamma. Okay.
Yep. I think whether you're doing density or level, kind of the thought process applies for using Cobalt 60 or the Cesium-137. Kind of on the right side of this slide, we'll say, is what you'll see is the detector, and so you can do kind of a length-based detector, which is typically used for a level measurement, or you can do kind of a shorter one for maybe just a point switch. You want a high-level alarm, low-level alarm. Why would a customer look to use a nuclear solution as opposed to putting a different technology in there?
Typically, I'd say the reason you use nuclear is because other things just aren't working and they're not giving you the results that you're looking for. So, usually, kind of the way I look at a nuclear measurement is it works when the other things don't. So, if you have something that has a lot of process buildup, for example, and it's stopping up capillary tubes, or maybe a radar's just not right for this, or it's just causing a lot of problems. Nuclear is non-invasive to the process, so it's on the outside of the vessel, which is pretty cool. I mean, you don't have to actually put it into anything. In most cases, sometimes for different measurements, we might actually put a source into a vessel. But
so is it safe to say? I mean, typically where we'd look to use a nuclear solution is maybe other instrumentation is not really working just on the technology side, or maybe the process itself is too aggressive to install something in.
The process, I would say.
Like high temperature, high pressure. So for example, a coke drum, maybe, you're not really going to put another piece of instrument inside there that's going to survive that, right? So
right.
That's and kind of to your point, Joey, the benefit is the nuclear stuff is typically all external, so it's easy to work on, and you're outside of process, which can be a big benefit.
Right.
So here on this diagram too, so we don't get too into the weeds, what we've got is a typical level application, let's call it. So you've got the source on the left side there emitting gamma radiation across that vessel. The detector on the right side is actually measuring those counts of radiation.
Right.
What happens is the process fluid in the vessel comes up, it'll basically block that radiation. So if we had 0% level, or the vessel's totally empty, right, then what that detector is going to see is 100% of the expected counts.
Correct.
If that level comes up all the way to 100%, it's going to block basically all of that radiation.
Right.
And the detector is going to see 0% radiation. in general. So as that level moves up, the radiation decreases, and so this detector is measuring radiation, but really from there we're inferring either a level or a density.
Correct. Yeah. So like in this picture, that's a looks like a continuous level measurement for us, and this particular one is 45-degree collimation. So what that means is that's the beam angle at which the radiation is coming out. The radiation, the capsule itself is installed inside of a source holder, and it's omnidirectional. It can go, radiation is just going to go whichever direction it's going to go in, right? So they cut a hole at a specific angle to direct. It doesn't, I wouldn't say the word focus because it doesn't increase it going that way, but it more just directs, only allows the radiation to go in that one direction. And so in this one's like a 45-degree collimation. They have some of them that are, I think Berthold has, don't they have some rod sources, don't they? And then the rod sources are just shooting it evenly across the vessel. And they linearize the radiation in that rod source, which is kind of a cool thing as well.
Yeah, and a little bit further down, we'll kind of talk about what a calibration looks like for one of these. But I think, in terms of what's on this slide, you're really looking at what is the information required to make this measurement successful. Mm-hmm. So, the top point is you got to calculate the distance.
Yeah.
That matters because if you double the distance from a radioactive source, it is now 4 times weaker at that point, right? So when you're installing one of this, you got to know, hey, how far is it from my source to my detector? That's one key thing. You got to look at all the material that the gamma radiation is going to pass through, because that's going to weaken it as well, right? Mm-hmm. So what are my vessel walls made of? How thick are they? What is the insulation made of, if there is any? And what is the density of the process, and what's going to go on with there, right? So anything that the gamma radiation is passing through is going to affect the counts on the other side. And really, when you kind of know what's your vessel made of, what's going on inside, and really the distance you got to measure, you can basically figure out, hey, what source activity do I need to get to this other detector on the opposite side and make this measurement, right?
Correct. Yeah, and it's basically an engineer solution, so all that's figured out for you. One thing, and I don't know if we're going to get into this, I may be jumping ahead, but in service, we always say geometry is everything and radiation doesn't lie. Mm-hmm. And I was kind of going back to that last slide, that last picture with the radiation coming out at a 45-degree angle. It's all about that. It's all about getting your angles right and your distance and everything like that. And the radiation itself is physics, so it is what it is. It's not going to change on you. It's the only thing that's going to change it is pretty much the outside influences.
Yeah, so I think, Joey, to your point, right, we're saying this radiation-based technology, it's bound by physics. So if you've got a known source activity on one side and you get to the other side and you're measuring that with a detector, it's going to tell you what's going on in that vessel. Right. And maybe you agree with it, maybe you don't. And Joey, I know you've got an example of where maybe the radiation didn't lie, although from your perspective it was a little wacky at first.
Oh yeah, it'll always, it's funny from the service end, you always have to remind yourself that saying I just said, radiation doesn't lie. I mean, there's been several instances where we go out and I know one in particular where I went out and operations is telling me that this vessel is empty, this vessel is empty, this vessel is empty, and I'm looking at it and I'm checking it and I'm like, it's full. Like I'm not getting anything across here. And they're like, hey, my sight glass is showing empty, everything's showing empty. There's no way. And I'm like, it's full, And then I could tell that because I'm using a handheld Geiger counter. I'm using one of these guys, okay, and this will give me the amount of radiation. And my gauge sitting on the side of the vessel and this are telling me the same thing. And I ask them to move level around a little bit, and they're like, well, it's not really going to move because it's empty. I said, well, drop it anyways. And then I could see counts. I could see the radiation changing. Mm-hmm. And to me, at that point, it's like, okay, I see it. Now it's a matter of just kind of convincing people of what I see. And that's happened. There's also been circumstances where I'm not seeing any radiation across, and come to find out, something in the vessels happen. We've had in a distilling tower, we've had like trays fall, and they end up in there, and the gauge sees it, and you don't really know what that means at first. And as time goes on, through troubleshooting and process elimination, you find out what's really happened. But it's usually telling you something, whether you believe it or not. It's there and it's telling you something.
Yeah. So basically, in that case, you really use this technology to diagnose that, hey, something happened inside this vessel, and it wasn't necessarily process related. It was a mechanical failure, right?
Right.
That's not what this technology is designed for, of course.
Not at all. Not
but
at all.
I mean, just to Joey's point, right? The radiation doesn't lie. So
it's
bound by the law of physics. So
correct.
Yeah. No, that's cool, and I'm sure. Well, finding a fallen distillation tray wasn't cool for.
No.
Yeah, but
that's the last thing they want to hear. So that's the last thing anybody wants to believe. But.
Yeah. Well, so on this slide, what we've got here is, if you kind of refer back to earlier, we talked about the photomultiplier tubes, and this is really kind of the core of how these detectors work. And what's great about Berthold specifically is they have one of the largest photomultiplier tubes on the market.
Right.
Why does that matter, right? And I mean, really, the biggest thing is you've got this scintillation crystal that lights up in the presence of radiation. And no matter how big that crystal is, you're somewhat bound by the size of the photomultiplier tube, because that light is only converted to an electrical signal based on what the photomultiplier tube can see. So what that means is the bigger the photomultiplier tube in general, you're going to get a higher count rate. And that really leads to an increased sensitivity. And we're going to kind of go into...
Yeah, it's high resolution.
Yeah, so, the high resolution, exactly.
I want to say they have, I want to say it's a 2-inch PMT, photomultiplier tube. And one of the things that relates to is that's the amount of, without getting too far into the weeds, there's a certain amount there's a coating on there, and there's a certain amount of electrons that are on this coating, and as light hits it, it degrades. Okay, and with having a 2-inch PMT, you're going to get for an instance, let's say an X-ray hit, really high count hit, that could cause some degradation of a PMT, but because you have such a large one there, it's not going to degrade nearly as much. It's going to be almost insignificant, and that's really one of the big advantages that I've seen on these so far.
So basically, the ability to basically extend the life of the photomultiplier tube,
right,
and then also that increased sensitivity are kind of 1-2 punch.
And when you do have these events that do affect your radiation measurement, they're insignificant. They don't really. It just takes a whole lot more of them to really make a significant difference.
Yeah, and I think we've been talking a lot about these scintillation crystals and photomultiplier tubes, and you really held up the Geiger-Muller counter. But do you want to talk about the historical technology that was used for maybe the measurement? The gas ion chambers and kind of the advances with the scintillation stuff.
Right. So, I mean, originally, and for those of you that may have been around a while, we used to have the ion chambers. And ion chambers they were good. They worked great for a long time. They're basically...
They detected radiation, right? So they worked as designed. Yeah.
Correct. And I think one of the big drawbacks on having an ion chamber is you really required a lot of radiation. So we had a lot larger sources out there, and those larger sources are going to cost in order to read the radiation on the ion chamber, you might have had like a millirem or 2 millirem. And when we switched technology to scintillator, I'm holding a Geiger-Muller tube out, and actually a lot of the switches, they had the GM tubes, and those switches also required higher radiation counts. Scintillator, this is a small scintillator, this is a 1/2-inch scintillator, but scintillator crystal is going to be much more sensitive. This is going to be the light going through, and it's changing it to counts and light pulses and everything, and a lot more sensitivity, and that means I don't need as big of sources.
So in general, right, like the rule of thumb I've always heard is about 200 times more sensitive, right?
Yeah.
So there's a big sensitivity increase.
Difference.
So if we look at it through kind of the lens of Berthold, right, because a lot of these nuclear measurements have been out in the field for a long time, and maybe originally they were designed with for a Geiger-Muller tube. So we've already talked that's less sensitive. It's a huge source, and we talked about whether it's cobalt or cesium. There is a half-life. It is decaying, And the great thing with the scintillation technology is you can repurpose these existing sources.
Correct.
In some cases, you even have to shield them because they're so strong.
Oh, yeah.
But there's an advance in the safety of the measurement, and we'll kind of get into safety a little bit farther down because you're utilizing less radioactive sources, so they're safer to be around. So that's one benefit of just scintillation technology in general. Mm-hmm. And then if we go back to, hey, Berthold's using this really large photomultiplier tube, that's making it even more sensitive as a detector. So once again, you can decrease the source size even further.
Right.
From a safety aspect, you can use basically some of the smallest sources out there,
right,
and still get a quality measurement, even more so than any other manufacturer because of the size of the photomultiplier tube, right?
Right. And be able to have more sources on your license. Licenses are usually good. Radiation licenses are good to a certain amount of activity that you have inside of whatever facility you're using them in, and being able to use lower levels of activity, lower source activity, I can have more of them,
mm-hmm.
So.
Yeah. So, and we're going to talk about why does elevated counts of radiation matter, and really it comes down to resolution. So, the example here is if I gave Joey a yardstick and it only had, a couple markings on it, and here we're working in meters, but whatever units
maybe
you want to
imagine.
Maybe
every foot or something,
Yeah, it's marked every foot, and I say, hey, tell me to an eighth of an inch, Joey, how long is this table? If I give him this ruler, he's really going to struggle. And I think if we kind of advance, well, if I give him a ruler that's marked off maybe quarter of an inch, he's going to get closer for sure.
Yeah.
But if we go all the way down to this kind of fine style ruler here, Joey with a high degree of accuracy is going to be able to tell me exactly how long this table is, and that's really what we're talking about with resolution, right?
Right.
How tight is your measuring window, and if you are working with 100 counts of radiation versus 10,000 counts of radiation, that's kind of what we're talking about. So
right.
More counts of radiation can lead to a higher level of resolution, and we'll kind of go into that here.
For sure.
So what we've got pulled up here is a trend. So on the y-axis, basically you've got your level, and you're really kind of looking at counts of radiation is what's trended, and on the x-axis you've got time. And a lot of folks, if you look at this, myself included, you're kind of going to think that the trend does a little something like this. So it goes up, and it goes down, and kind of levels off, right?
So are these, that green line, is that raw counts? Or
Yeah.
Okay, raw counts.
Yeah.
So that's just what it's seeing, no filtering.
Mm-hmm. And so, I think for myself and Joey and probably most folks who would look at this trend would probably imagine it follows something like that red line.
Yeah. So that red line there is that's actually what's coming through the detector. So raw counts versus the detector itself,
mm-hmm.
right? Okay, I got you.
What actually happened is, if we can redraw this red line here, which I'm gonna click and catch it up here, is it's a bit of a step change here, and it's really hard to tell. I mean, if you look at the green trend and then you look at the red trend, which is actually what happened in the vessel,
mm-hmm.
It's hard to tell that. And so how do we know this happened? Well, what happened is we had a detector that was far more sensitive mounted in the same application. So basically we're getting 5 times the count rate. And when you look at this blue one, you can really kind of see that step change that we're looking for here.
Right. Okay. So when we look at the one with the higher resolution, you can see where it actually moved up in the average counts if you look at the center line. Okay.
Mm-hmm. So
yeah, I see that.
Yeah, that increase in count rate increases your resolution, and from there it's much easier to draw conclusions about what's going on in your vessel, right? And that really goes back to, at the end of the day, we're measuring radiation, with our partners Berthold, and if it will tell you something that's going on in the vessel, but
Absolutely.
Obviously the higher count rate gives you better resolution, and you can draw a better conclusion on what's going on inside the vessel, right? So I'm just going to make sure that we're caught up on the delay here, and if there are any questions, feel free to jump in. I will say, while I'm waiting on this to catch up, this is kind of a multi-part series we're going to do on the radiation-based measurements. So if there's a topic you all would like to see us go into the weeds on, really today we're kind of saying 30,000 foot overview.
Oh yeah, we're just talking about the basics on it.
Yeah, if you want to go application focused, or if there's a topic that you'd really like to see, feel free to reach out to us, and we're happy to kind of go into that.
Yeah, if you want to see more focusing on maybe installation or commissioning, or how to set one up, then yeah, we'll be glad to design our future ones around those.
Okay, so when this next slide here pops up, what we've got going on here is a rough overview of the Berthold portfolio, the different. Oh, we went a little too far on.
We got bananas.
Yeah, we got bananas, so that's a spoiler. When this slide jumps back, what we've got here is a little overview of the Berthold portfolio, the different style detectors you see here, the different source styles, and really what you see on the right is the result of what you can do. So with the point detector, with the rod style detector, the narrow beam, fan beam, rod source flange, what you're really looking at is a bunch of different options to optimize the solution. So depending on the application, Berthold really designs the solution to meet the application. So what you're not trying to do is fit a round peg into a square hole, and you can somewhat get by with that in a lot of cases, but with Berthold, we're very fortunate that they can really offer what is the best measurement for this application. And so, when in terms of control, safety, efficiency, on the end user side, I mean, there's a huge benefit to knowing that when you're installing, this equipment, that it's the best of the best, right?
Right. Yeah. Oh, yeah. And on their, I guess their continuous level, we can add to a continuous level, right?
Yeah.
So, kind of a neat thing that they have is they have these extension pieces. So if you have a specific length, and help me on the links here. I want to say it's like a meter or 3 meter.
1 meter, 2 meter. Yeah.
Yeah, and then you can just add a meter. Basically, you connect it up to your old one. So if you have one this long and you want to make it this long, you just connect them together. And you can have them on the shelf, which is kind of cool.
Yeah, and so what Joey's getting at there is you can do that in the field. So from a stocking warehousing perspective, you really only need a couple parts, and then no matter what the application is, you can kind of build the length in the field. So if you get in a bind and maybe a detector fails on a critical application, hopefully you've got a redundant measurement. But if you're in a bind, you can always go run to the warehouse and assemble the detector you need right there on the spot.
Right.
So you're locked and loaded, and you're not running blind on some of these critical applications.
Right. So kind of yeah.
So now we'll, since we already kind of spoiled it, we'll jump into
our bananas.
Yeah, into the banana. Why the banana? So for those who aren't aware, bananas are slightly radioactive.
Yeah.
Very, very tiny. 0.1 microsievert is the dose typically in a banana. And so you're probably thinking, hey, why are Joey and Phil showing me a picture of a banana?
Right.
Thankfully you guys are eating right now, hopefully, so you're not too hungry.
Right. Somebody out there is in the middle of eating a banana right now.
Yeah.
Probably just put it down.
But the question that comes up a lot is, and that we deal with a lot, is how safe are these measurements, right? You're talking about a radioactive measurement. I don't know about you, but I always think of the Incredible Hulk, or something like that. Am I going to turn into the big green man? But
I wish it hadn't happened yet.
What we want to talk about is there is a degree of risk, and we take it very seriously.
Right.
But these things are designed in a way to optimize safety. Because Joey's going out and working on these things, so we're not going to sell a solution that is unsafe.
Right.
And there's protocols to follow. But hopefully, when we share some of these examples, we can illuminate the degree of risk you're undertaking. So, Joey, typically when a source is designed, that radiation is traveling one direction through the vessel. We want to aim it through direct. So can you tell me what are some typical measurements both on the source side, and then let's say you're on the detector side? How much radiation are you being exposed to?
So the manufacturers, Berthold in particular, 2 millirems per hour is what they're going to be. Probably 90% of their gauges on the source side. That's not even connected to the vessel. That's just sitting out. And if you were to measure 1 foot away with the source closed, they're not going to exceed 2 millirems per hour. Okay, 5 MR is the absolute. Like they won't even ship one that's over 5.
Yeah,
and
that's a U.S. regulation, correct?
Yes, yeah. This stuff is regulated, and even in the field, whenever we do our safety checks, all of the TechStar service team, we're all radiation safety officers. So we've been through extensive training on the safety side of things, and how to test for radiation, how to test for radiation leakage. Never seen it happen, but we test for it every time. And it's, I guess 2 millirems per hour, to really put that in perspective. Most of them, when I say the max is 2, you're usually seeing less than 1 millirem. If you were to go 1 foot out, most of them are less than 1 millirem. You might even have a lot of them. There's times when I don't see anything on the source order itself. These manufacturers take a lot of pride in trying to keep these sources low, and that's part of the reason why we have such a sensitive detector, is so that we can have such low energy levels.
And then, so what about on the detector side? What type of radiation can we expect?
So on the detector side, in the old days, I'm going to talk about the old days first. Old days, you might have 1 millirem, 2 millirem, okay, and that's going to be your ion chambers. And nowadays, we get down to 0.05 millirems per hour, and we're detecting at such a low level. 0.05 is, give an example. This is slightly off subject, but not. Went out fishing with my kids over at the Texas City Dike, and you know how you have all these big granite boulders everywhere, and granite is a natural form of natural curing radiation. Radiation is nothing but the decaying of an element. So as an element decays, it shoots out basically energy out of the nucleus of the atom, and that's what radiation is. And anyways, I was just curious. I happened to have my scintillator in the truck. I'm like, I wonder what kind of radiation this thing, if I can even pick it up. I went out there, and these granite rocks were putting out almost 1 millirem per hour. And I'm thinking, how many days do people sit here on top of these things fishing for hours and hours at a time, and then you have that much radiation? So,
well, and so if I'm hearing you kind of on the installation side, so at the worst on an install, we're probably 2 millirems per hour at a foot away, right?
Well below those kind of levels.
And I know if you go get a chest x-ray at the dentist, that's 2 millirems like that.
Right.
So, I mean, you know, there is a level of risk with this technology, but it's extremely low. You know, there are protocols, everybody's aware of it, and you know, I think our message here is, in your daily life, you're probably exposed to more radiation than you'd realize or care to know. I mean, if you fly a lot, you're exposed to radiation. You know, I guess if you ate a tremendous amount of bananas, you could up your radiation dose, right? That's
they say that if you ate a banana a day, that's 4.2 millirems a year. Okay, so even banana, something that we consider healthy and good for us, it has a certain, it's all around us. So the message is not that we don't have to be careful with what we put inside of our chemical. We absolutely do. What's in our plants and what's in our processes, we have to take it very seriously, and it is radioactive. But we take all these precautions to keep these levels low enough that they're at such a minuscule amount that it really just doesn't matter. And even as we're going in and we're doing our checks as technician, we take it really, we treat it as if it was really high levels. We do all the documentation as if it was high levels, but in most cases, it's very low levels.
So, yeah, I mean, I think, you know, to Joey's point, we as TechStar and, you know, with our partners, Berthold, are here to support. So if there are any questions when on the measurement side, you know, we can make recommendations for what is the best technology. And assuming it is a radiometric measurement with Berthold, you know, what we can do as both Berthold and TechStar is assist on the safety side. Obviously, we're going to help engineer it. And, you know, I think Joey and his team can specifically help with any safety, on-site safety.
Absolutely.
And then I think, you can help calibrate, can you not?
We can. So our team, the different things that we do is we can do full commissioning. So the full commissioning of the source. We can do the packaging of a source. So by DOT regulations, any source that if you were to be transporting, it has to be packaged by somebody that's certified to package for DOT. We have those certifications, and we basically handle it from pretty much beginning to end. We bring the crates out that need to be out there or have them sent to you, and have you guys assist getting it into the crate, and then we do all the paperwork and all the stickers and everything that's required. Commissioning itself, we do the full commissioning from beginning to end.
So what is give me a 30,000 foot overview of what a calibration looks like.
Sure.
So you install this, and then what?
So once it gets installed, we go into the field, and usually the first thing that we do, like we said, that radiation it doesn't lie, right? So we try to do a source, basically a vessel survey. So first, and this is for paperwork purposes and for future analysis, we'll go through, and every 6 inches or so, I'll go inside of this vessel and I'll see what my radiation levels are, and I'll record that in my paperwork. And what that does for me is, say later on, 5 years from now, you're back down in the same operating conditions that you were when I did this check. We go and we check it again and we see something different. Now we know something's changed. Okay, something in the vessel has physically changed, and we can relate that to, hey, maybe I had some buildup happening in here, or what's happened. It just gives us a clue. So that's usually the first thing we do, is we just do a survey. Second thing we do is we get up, whenever we do a calibration, we need to be to what we call a process zero. Okay, so a process zero meaning we have the vessel at its normal operating conditions, pressure, temperature. If you have let's say a cooling jacket of some kind, whatever is going to be circulating during our normal process, that's circulating, and we take a count reading at that point, and we see how much radiation is coming across the vessel. Well, that's our zero. And then from that point, we can do it two ways. Okay, if we're not able to really move level, then we can just close the shutter and do 100% and consider that would be 100%. There's no radiation going across, or that'll give us a very repeatable measurement, not necessarily super accurate, but very repeatable. And if we're looking for high accuracy, then we'll raise it up every 10%, 20%, and then take another reading and enter those to build a linearization curve on the in the software for the level measurement. So we know 10,000 counts is empty, 9,000 counts is 10% full, and so forth, so on.
So if I'm hearing you, basically one of the advantages of these nuclear measurements is you can basically calibrate while the vessel's online, and it can be as simple as a 2-point calibration.
It can be,
and obviously it's very process dependent. But in general, it's maybe whatever you're operating at, and then maybe a closed shutter.
Yeah.
And that will give you a lot of repeatability. And then depending on the level of accuracy that you're looking for, maybe you got to do some different things.
Right.
And so
we always prefer a process zero.
Yeah.
There are cases when it's impossible to go down at this time. And let's say they're running. What we'll usually do is say, hey, operations, how low can you safely take this process? And they take it to that level, and we take a reading there. Can't guarantee what the accuracy is going to be under that. The gauge will calculate that out. But operations like I'm not going to go down there. I'm not going to go to that point until we go down. So they're not too concerned about it. Then I'll do my 100% level or higher level reading, and then we've got an accurate measurement. So we don't have to be completely down in order to set one up. We can do it with it running.
Yeah.
We just need to go as low as we can.
Yeah. So depending on the process, then
it's very process dependent on our.
Yeah, you may not be able to shut down. We understand that, and we can kind of calibrate around that. And Joey and his team can be a key piece. What if Joey? Let's say you go out, you help with the initial calibration, everything's running smoothly, and the site wants to own a bit of it themselves moving forward. Can you help with training? Can you help
Absolutely.
with teaching? Can you tell me a little bit about that?
Yeah, so we actually have a training facility here at TechStar, and the room that we're in right now is kind of this is where we do our lectures. We also have a full lab next door that has a lot of equipment in it, so we can do training there. And also, all the technicians at TechStar are more than happy to have technicians or engineers working with us in the field. So if we're doing these calibrations, many of the time I've sat with them and even had the technicians themselves or the engineers themselves perform the calibration through supervision.
So is it safe to say, and right now what we've got displayed is kind of the classroom setting, but depending on the learning style of the group interested, we can sit down in a classroom style,
absolutely,
kind of geek out about theory, or when we kind of advance to this next slide here, we can also do a lot of hands-on stuff with our process lab, which is just next door.
Right.
So really we can do a combination of both, right? So a combination of classroom, a combination of hands-on laboratory.
Absolutely.
And then also on-site training. So if depending on where the facility is located, if you're not close to one of our offices, we can obviously come to you and do all of this. Is that
Yeah, that's
safe?
absolutely true. So if you just want to say, hey, my team, I need to get my whole team trained up and know a little bit about nuclear. We need to know theory. We need to know how to set these things up and what to do when this unit goes down at 2 a.m. and we need to prove what's going on with the gauge. We have a demo set up, and we can sit there and we can work through the problems like guys setting them up in the classroom setting to where we're not messing with a live process in the field with a risk of upsetting a process. We can do it inside of a classroom setting and get them familiar with setting up the gauge and with going through and how to do the commissioning and how it works and a few troubleshooting tips. So that's absolutely something that we do.
Well, we appreciate everybody attending this morning. I mean, I think what we wanted to do is kind of give a high-level overview of the technology. Mention that we're very excited to work with our new partners, Berthold. They've got one of the most sensitive detectors on the market, which gives us a great tool to support you guys as TechStar.
Right.
Whether it's radiation-based measurement or any type of technology, I mean, we are your solutions expert. We're here to support you guys. So if there's anything we can do to help, please reach out. I didn't see too many questions this morning, but if you've got an application you want to discuss, please feel free to reach out. Or if there's another topic, like I mentioned, this is kind of the first one of a multi-part with the nuclear-based measurements. So moving forward, what we're going to do is go into some application-specific ones. For example, coke drums. Talk about how to deal with NORM, naturally occurring radioactive material. Talk about your separator measurements, whether it's an alky or a desalter.
Right.
And if you folks have any ideas, we're more than open to put together something on it. So hopefully this was a good little teaser today, and we can kind of go in depth on some more specific stuff because it's there's a lot to this subject. But thank you all for attending. Joey and I appreciate it.
Thanks,
and,
guys.
If there's anything we can do, please reach out.